Okay, so we're going to start today and continuing with launched projectiles. So let's take a look at what this would look like, the beginning of the motion. Okay, we have a soccer ball that's being kicked from the ground, okay, at some angle in the upward direction. Okay, the angle is 32 degrees, so it's going to go from the horizontal. And what would the hypotenuse of the triangle be? What would the value of that be? Good. Our initial velocity goes here, because we're going to break this initial velocity vector down. And we're going to break this initial velocity vector down into x and to y components. So what would I label the sides of this triangle then, if we're breaking down our initial velocity vector? What would this side right here be called? V sub yi. Okay, and the bottom side would be called what? Good, V sub xi. So now let's go ahead and solve for those so that we can use them in our equation.
These are the ones where once you find like the components of this, you're done with the triangle.
That's right. Okay, so to solve for V sub yi, we do what? Yeah, good, sine. So we take 6.5 times sine of 32.
Yeah.
And we get what?
Yeah, I don't like how they do that.
It just gives me a headache because all the numbers are all
3.4. Okay, and what about V sub xi? Good, 5.5. So we take 6.5 times cosine 32. And we get 5.5. So now we're done with this triangle. Okay, we're done with the 6.5. We're done with the 32 degrees. Those will not go anywhere else in our problem. Okay, now we're starting with our regular kinematics equations. So if we start our list over here, we know V sub yi equals 3.4. We know V sub xi equals 5.5. Okay, what else do we know? What else was given to us in our problem?
V I equals 0.
Yeah, V sub, no, what did you say?
V sub I equals 0. No. It's not V sub I. It's was it Y sub I?
Yep, y sub I equals 0 and x sub I will both equal 0. Okay, and the reason they both equal 0 is because we start at an origin. Okay, and at an origin, our coordinate point should be 0, 0. We also know that vertical acceleration is what? Good, negative 9.8. Anything else we know that's given to us? Okay. So we want to know how long total this ball will be in the air. What do you think a good way to go about solving that would be? Yeah, well, we want to find time, okay. What equation do you see that we could use to solve for time? Yep, we could use the y sub f equals y sub I. That's going to make us use the quadratic formula, though. Okay, so I think there's a shorter way to do it. We're going to talk about why we can use the first one, okay? Why we can use it. Okay, what we want to see with the first one is we're talking V sub yf equals V sub yi plus at. Okay, because right now the only things we know in this equation are V sub yi and a. What if we look at the path of this ball just to peak height? If we look at the first half of the path.
Then your final will be 0.
Exactly. Then this right here would be 0. Okay, so what would we have to do to time then at the end of our problem? We double it. If instead of using the quadratic formula with this other equation, with the y sub f equation, we can use this one. And we make this 0 because we're looking at the first half of the path. Okay, so we're looking at time from here to here. Okay, because when something reaches its peak height, its velocity vertically is 0. Okay, so here we're just looking at the first half of the path. Yeah. So if we choose this to solve for time, we're going to make this 0. V sub yi is 3.4. Acceleration is negative 9.8. And we're going to solve for time. So we move 3.4 to the other side. We get negative 3.4 equals negative 9.8 t. And how do we get t by itself? We divide by. So time is going to be what? 0.35. However, this is the time. This is the time to what point in the projectile?
The middle.
This is the time to peak height. Okay, so let me get rid of some of this here.
So 0.7.
Yep, so 0.3 is only our time to peak height. So we need to take it times 2 to get our total time.
I know, I'll forget that.
Okay, so we took our time in the last one times 2 to get 0.7 for the total time. But here, if we're trying to find out how high it will go, what's that mean we're trying to find? YF at its peak height, right? We're trying to find peak height. So that means what time will we use then if we're trying to find the peak height? Exactly, we'll use the 0.35. Okay. So tell me an equation we can use here to find peak height. Yep, we'll use this one. So we're solving for our peak height. Y sub I is 0. V sub yi is 3.4. Sorry, I kind of ran out of room. Should your y final be negative here like it was for our rolling projectiles? No, because we're going up. It's going up.
Are you even writing this in the last one? This is all the text.
What'd you get? You don't have a calculator.
Maybe I will, because I'm here.
I didn't plug it in.
Plug it in, plug it in.
I think I got like I'll plug it in.
Okay. Yep.
Can't see that far.
0.59 meters.
Okay, we already got the answer.
Solve for x sub f on your own, which is our horizontal distance traveled.
Well, so it would be,
So do you use the
yeah.
What do you think? Do you think we're going to use total time or peak height time?
peak
Total time. Because we want to find out how far totally did it travel horizontally. So we need to use the total time here.
But for this one, did we use half of it?
Yep.
So what was it? 3.85. So what did we say before?
For the second part, we're looking for x sub f.
Excellent.
Our final horizontal distance. Okay, so what do we get? 3.85. What's our units then? Meters. Okay, so this ball, if you think about the trajectory or the path that it went on, it didn't go very high in the air, right? It only went 0.5 meters in the air, 0.59. How far did it go, though? 3.85. Okay, so it went not very high in the air, but pretty far along the path. Okay. Do the next one on your own. We want to find out how long until the cannonball hits the ground, so total time, and how far did it travel horizontally. So we're solving here for time, and we're solving for x sub f. Okay, so we walked through this equation here. We chose 0 because it's at peak height, which means we found our time for the first half of the trip as 4.7. We multiplied it by 2 since we were looking for total time. So time for the whole trip was 9.4. We're going to plug that in over here, multiplied by our initial horizontal velocity to get 717.2 meters as our total horizontal distance traveled. Everyone agree or not so much?
That was perfect.
All right, so relative velocities. So relative velocities are observations or viewing of speed in different reference frames or frames of reference, okay? So this is like I'm standing here, a car is coming by me, I think it looks like it's traveling this speed. Or I'm sitting in a car and someone passes me and I think they're going this speed. Okay, we're talking about frames of reference that are different than just standing on the earth or being in one particular spot. Okay? So we're going to look at an example of two trains traveling towards each other at 80 kilometers per hour. Or two objects. Doesn't necessarily have to be a train, okay? Two objects traveling towards each other at 80 kilometers per hour. Okay, so if I'm standing beside the tracks and I see both of these trains, they both look like they're traveling 80 kilometers per hour because I'm standing still. Right? They both look to me, if I could calculate that in my brain just by seeing it, I would say that they're both traveling 80 kilometers per hour. Okay? Because I'm standing still and I'm able to see both of them. Okay? So the reason that this is because you're moving 80 kilometers per hour, they're moving 80 kilometers per hour, closing in on that same distance, okay, in half the amount of time. So it looks like we're going twice as fast, okay? So if you're driving down the highway and you're going 70 miles per hour and you come up and you meet a car in front of you that's going 55, how fast do you think they are going?
So slow.
Right? It feels like they're going so slow. It feels like they're going about what? Any guess?
Half the speed.
Fourth.
A fourth of the speed, half the speed, okay? How many of you think half the speed? How many of you think, raise your hand. Okay, so that's why when you come up to someone and you feel like they're going 15 miles an hour, that's because they're going 15 miles an hour slower than you. Okay, so that's why it feels like they're crawling, because you are moving at such a great speed, they're moving at a lesser speed. So the difference between those is 15. That's how much the relative velocity to you would be. Okay, so relative to you, they're traveling 15 miles per hour. Okay, that's called same line velocity. The examples with the train, the example with car drivers, those are both examples of same line velocity. Okay, they're traveling in the same path. They're not coming from different angles. They're traveling in the same line. They could be going in the same direction and opposite directions, but they're in the same path. So if we come across things that have relative velocities that are not in the same path, we're going to have to start using vector addition again. Do you remember what vector addition is?
Tail to tip.
Yeah, tail to tip. Okay. So if I have a vector here, 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 okay, I have all these vectors. What is this new vector called? This one from origin to the end. Yeah, it's called the resultant vector. Okay, so all of these vectors that made up our path kind of get us to our final end point. And this resultant vector right here goes from the origin to the tip of our last vector. So the trickiest part of this chapter is learning how to draw this resultant vector and finding out what it's going to look like. Okay, relative velocities are labeled with two subscripts. The first of which refers to the object. The second references the frame in which it has the velocity. Okay, so it's kind of who sees the object moving at that speed. And this will be a little bit clearer. Okay, so that in order to get to the resultant where we want to be right here, we've got to leave the shore at some angle so that the current will help push us back to where we want to be. Okay, so this is a lot of solving Pythagorean theorem, using second tangent to find the angles, things like that. Okay, this is just the vector addition that we'll go through here. Velocity of boat with respect to the shore, which is right here, our resultant, is the addition of these two vectors. Okay. It's a lot easier when we get into problems with numbers, I think. Okay.
So this is just kind of like an explanation.
Mm-hmm. We're going to plug in numbers here in just a second. Okay, the boat speed in still water is 1.85. If the boat is to travel directly across the river, who has a speed of 1.20, at what upstream angle must the boat head?
Are we always going to use boats?
No.
That'd be nice.
Okay, so here it gives us two sides of our triangle. It gives us the velocity of the boat in the water, which is 1.85. It gives us the velocity of the current, or water, with respect to the shore as 1.2. and it wants to know this angle.
It's time to do some negative tangent, right?
What sides of the triangle do we have?
The hypotenuse and the opposite.
John.
Hypotenuse and opposite. So we need to use second sine. So here we're going to go sine -1 equals the opposite side, which is 1.20, over the hypotenuse, which is 1.85.
40.4.
40.4.
Really? Hmm. Haven't done it yet.
Okay, so what this problem is telling us is that in order for this boat to end up exactly across the river from where it started, it must head in the opposite direction of the current at a 40-degree angle. Okay? If we break these problems down and think about them in real life, this should make a lot of sense, right? If you want to fight the current to get exactly across the river from where you started, you need to leave at an angle that's opposite of the current flow. Okay? Does that make sense? That should, I think that should, kind of common sense make sense. They're traveling east at a speed of 4 meters per second. She rolls a marble with a velocity of 0.75 meters per second north, straight across the deck of the boat.
So on the last question, we're looking for the 40.4.
What's the velocity of the marble relative to the water? Okay. So here we're going to say that it goes east. Okay, our original vector goes east. At 4.0 meters per second. The marble gets rolled north at 0.75. So we need to find the resultant of this triangle. Okay, so how do we find resultant?
Pythagorean. No.
Yeah, Pythagorean theorem. We're going to solve Pythagorean theorem here.
So are you always going to have to solve for the hypotenuse in these problems?
It might tell you this is the speed they want to be going when they get to this point, and in which case you have to solve backwards for one of the sides of the triangle. Solve for the hypotenuse and find the angle, and then we'll check in and see if everyone agrees.